Welcome, everyone. My name is Aspen,
And my name is David Gang.
and today we're focusing on a critical hardware vulnerability, CWE 1189, improper isolation of shared resources on SoC architectures. SoCs are vital components in modern electronics, but their complexity means security challenges, particularly in resource sharing. In this presentation, we'll delve into the implications of CWE 1189, its impacts on system security, and strategies for mitigation. Let's get started.
So CWE 1189 was on the 2021 CWE Most Important Hardware Weakness List. The weakness itself occurs when systems with limited pins or pads are forced to multiplex. Multiplexing the pin allows multiple functions on a single pin. However, it can also inadvertently share resources between trusted and untrusted agents. If they're improperly isolated, if they're improperly isolated. This is not a new weakness. The list is also unsorted, so the ranking is unknown. It is also not in the Kevra OWASP top 10 lists.
The type of weakness of CWE 1189 is a base weakness. Base weaknesses are weaknesses that, while abstract in nature, have still been sufficiently defined to infer methods of detection and prevention. Sufficiency for the base class requires either two or three dimensions to describe the error out of these categories: behavior, property, technology, language, and resource. Using more or less than two or three changes base to variant or class weaknesses instead.
So other related weaknesses are CWE 1303, which is a child of CWE 1189. 1303 is non-transparent sharing of microarchitectural resources. Since it is hidden, often leads to improper resource sharing, which means that potentially untrusted agents are able to access private assets. CWE 668 and 653 are both parents of 1189. 668 is the exposure of resources to wrong sphere, and 653 is the improper isolation or compartmentalization, both of which occur when a function, asset, or resource are improperly exposed to lower level privileges.
There are two weakness occurrences of CWE 1189. The first being CVE 2020 8698. Improper isolation of shared resources in some Intel processors may allow an authenticated user to potentially enable information disclosure via access. And CVE 2019 6260, the ASPEED AST 2400 and AST 2500 baseband management controller, hardware and firmware implement advanced high performance bus bridges, which allow arbitrary read and write access to the BMC's physical address space from the host. This CVE applies to the specific cases of ILPC2A HB Bridge Parts 2 and 1, PCIe BMC P2A Bridge, and Watchdog setup. So, some more details about these related CVEs. CVE 2020 8698. Improper isolation of shared resources on some Intel processors may allow an authenticated user to potentially enable information disclosure via local access. The issue was found internally by Intel employees. Successful exploitation of this vulnerability could lead to disclosure of sensitive information. And to mitigate this, Intel released microcode updates for the affected processors. As for the other, baseboard management controller device implements advanced high-performance bus bridges that do not require authentication for arbitrary read and write access to the BMC's physical address space from the host and possibly the network. Common configuration of the ASPEED BMC SoC's hardware features leaves it open to remote, unauthenticated compromise from the host and from the BMC console. This stems from AHB bridges on the LPC and PCIe buses, another on the BMC console UART, and the ability of the XDMA engine to address all of the BMC's MBus. Successful exploitation of this vulnerability could lead to disclosure of sensitive information, addition or modification of data, or denial of service. To mitigate the threat, NetApp released multiple software patches for the affected devices.
Consequences on security requirements. Confidentiality. There is a breach of confidential information, exploitation of unprivileged position, and access to higher level areas with private data resources. The effect on availability is that modification of a trusted user's shared resource by an untrusted user, denial of access to data by removing or editing systems, and the impact of functionality and access from unprivileged position. The integrity is affected by intentional degradation of shared resource functionality, unintentional access by malicious users causing damage, and scope of weakness affecting resource integrity. So some weakness examples are in the hardware root of trust in the system on a chip design manages the hardware security and is mapped to the address space of multiple processor cores. The static random access memory acts as a mailbox of sorts in the root of trust, which distinguishes trusted and untrusted access to memory regions. The weakness is that the software can access the memory map to all the cores and may run different privilege levels on untrusted cores, since those cores are able to communicate with the SRAM mailbox. To mitigate this issue, information shouldn't enter or exit the shared region of SRAM through the HROT and iFace.
And this is just a diagram to picture this example.
So the exploitation of weaknesses. Physical access is not required to exploit the weakness, as the exploit takes advantage of how the software and hardware manage separating trusted and untrusted agents. Exploitation can be done completely via software, as again it focuses on using the software and hardware improperly being isolated, and so the software can accidentally be used to access trusted areas. A single exploit may or may not be applicable to a wide range of devices, but it depends on the manufacturer's hardware and software implementation. If the mistake is consistently throughout their devices, then it should be able to be exploited with a wide range, but otherwise, if the hardware and software differ substantially, it is unlikely to be propagated through a wide range of device.
Detection, prevention, and mitigation are definitely possible for this weakness. One detection mechanism is automated dynamic analysis. This happens pre-silicon or post-silicon. Test access to shared systems, resources, memory ranges, control registers, etc., from untrusted software to verify that the assets are not incorrectly exposed to untrusted agents. Note that access to shared resources can be dynamically allowed or revoked based on the system flows. Security testing should cover dynamic shared resource allocation and access control modification flows. There aren't many recorded incidents of this weakness. Only 2 have been recorded, one in 2019 and one in 2020, both of which after the system was deployed. Otherwise, there is not sufficient info to determine the frequency for design and testing. The weakness can be prevented by ensuring that assets are properly isolated and that users are checked for proper authorization before allocating the asset for the user. For methodologies to prevent this weakness, penetration testing, vulnerability assessments, physical reviews are potential methods to find this weakness. And a mitigation method is separation of privilege during architecture and design phase. When sharing resources, avoid mixing agents of varying trust levels. Untrusted agents should not share resources with trusted agents. The weakness occurs during the architecture and design phase along with implementation. Mitigation can be achieved by isolating resources and ensuring that a check for proper authorization for the resource is done. Once the device is deployed, it can be fixed, but may require physical access depending on the physical implementation of the hardware resources and the severity of the weakness.
In conclusion, CWE 1189 exposes a critical vulnerability in system-on-a-chip designs. Improper isolation of shared resources. This flaw can lead to unauthorized access and compromise sensitive data, posing significant security risks. Addressing this weakness demands collaboration among hardware designers, software developers, and security experts to implement isolation measures. By prioritizing secure development practices, the risks associated with CWE 1189 can be mitigated, and the integrity of system-on-a-chip designs can be improved. Thank you.